On January 28, 2026, NASA announced that the James Webb Space Telescope had done something it had now done several times before, and yet somehow still managed to surprise the very scientists who'd spent years anticipating it. It had broken its own distance record again. The galaxy in question, catalogued as MOMZ14, sits so far away that the light Webb captured left it roughly 13.5 billion years ago, when the universe itself was only 280 million years old, a sliver of cosmic time representing about 2% of the universe's entire current age. This is the real story of MOMZ14, why it's quietly become one of the most genuinely unsettling results in modern cosmology, and why the scientists studying it keep using words like chasm to describe the growing gap between theory and what Webb keeps finding. To understand why a single distance smudge of light can cause this much trouble for cosmology, you need to understand what astronomers expected to find in this part of the universe's history before Webb ever launched. The prevailing models, built up over decades using our best understanding of gravity, dark matter, and the physics of star formation, predicted that galaxies this early in cosmic history should be small, dim, and rare. The reasoning was straightforward. Right after the Big Bang, matter in the universe was spread out almost perfectly evenly, with only tiny, subtle variations in density. Gravity needed time, a lot of time, to slowly pull that thin, diffuse material together into the first clumps of gas dense enough to collapse and ignite the very first stars. Those first stars then needed more time to cluster together into galaxies, and those young galaxies needed still more time to grow large and bright enough to be detectable at all. Based on that framework, astronomers expected that finding any galaxy bright enough to observe at a redshift beyond 10, a measurement corresponding to roughly the first 500 million years after the Big Bang, would be extraordinarily difficult, requiring tens of hours of observing time just to confirm a single faint marginal detection. Webb didn't just find a few of these galaxies, it kept finding them over and over, brighter and more numerous than anyone anticipated, at distances theoretical models said should be nearly empty of anything bright enough to see at all. MOMZ14 is simply the current record holder in that ongoing, uncomfortable pattern, and NASA's own description of it in the language of the official announcement, called the galaxy brighter, more compact, and more chemically enriched than astronomers had any reason to expect for an object existing so soon after the universe began. Let's break down exactly what that means, piece by piece, because each part of that description represents its own separate problem for existing theory. Start with brightness. A galaxy's brightness at these distances generally reflects how many stars it contains and how actively those stars are forming, burning, and dying. For MOMZ14 to be bright enough for Webb to detect and confirm at all, at a distance representing less than 300 million years of cosmic history, it needs to have already assembled a genuinely substantial population of hot, young, massive stars, on a timescale that standard models of galaxy formation struggle to explain. Then there's compactness, meaning the galaxy has packed a significant amount of that stellar mass and light into a comparatively small physical area, a structural feature that typically takes much longer to develop under conventional models of how gas collapses and organizes itself into a coherent galactic structure. The chemical enrichment finding is, if anything, even stranger, and it's the detail that seems to have genuinely startled the research team the most. Spectroscopic analysis of MOMZ14's light revealed elevated levels of nitrogen, a heavier element that isn't present in the earliest generations of stars, which are built almost entirely from the simplest elements forged directly in the Big Bang itself, hydrogen and helium. Nitrogen, along with other heavier elements astronomers collectively refer to as metals, only gets created inside stars through nuclear fusion, and it only gets released into the surrounding gas when those stars eventually die, either through calmer processes like stellar winds or through violent supernova explosions. Finding meaningfully elevated nitrogen levels this early in cosmic history means that MOMZ14 must have already gone through at least one full generation of massive stars, living out their entire lifespans and dying, seeding the surrounding gas with heavier elements, all within a span of time. Current models say should barely be long enough to form the very first stars in the first place. As the research team put it in their own published findings, this suggests that massive stars may have formed and evolved considerably faster in the dense conditions of the early universe than existing theoretical models currently predict. On top of all that, Webb's observations turned up one more genuinely unexpected feature. The region of space immediately surrounding MOMZ14 appears to have been cleared of the primordial neutral hydrogen gas that should still have been thick and pervasive throughout the universe at this early stage. In the standard picture of cosmic history, the process of clearing out that primordial hydrogen fog, an era astronomers call reionization, was expected to happen gradually, driven collectively by the combined radiation output of many galaxies working together over hundreds of millions of years. Finding a cleared bubble around a single galaxy this early suggests that either MOEM Z14 itself or its immediate surroundings was already pumping out enough intense radiation to locally punch through that primordial fog well ahead of the timeline most reionization models describe. Put all of that together, and you start to understand exactly why MIT postdoctoral researcher Suijian Shen, one of the study's co-authors, chose the specific language he used in NASA's official statement, describing what's happening here as a growing chasm between theory and observation regarding the early universe, one that presents compelling, genuinely open questions that the field now has to work through. That's not casual, offhand language from a scientist. It's a carefully chosen phrase from someone who studies this exact problem for a living, describing a real, widening gap between what our best physical models predict and what our best available instrument keeps actually showing us. It's worth being honest about how surprised even the Discovery team was by their own result, because their own public comments make clear this wasn't an expected outcome they'd simply gone looking to confirm. Yale astronomer Peter van Dokkum, another co-author on the study, told reporters candidly that while the team had been hoping to find some genuinely early objects in their survey data, he didn't think any of them expected to actually break the existing redshift record when they set out. That's a meaningful admission. This wasn't a targeted search engineered to produce a headline-grabbing result. It was a broader survey that happened to turn up something well beyond what even the researchers running it anticipated finding. MOEM Z14 also isn't happening in isolation, and understanding that context matters for taking its significance seriously rather than treating it as a single isolated fluke. It's the latest entry in a growing, increasingly uncomfortable list of unusually bright, unusually massive, or unusually chemically advanced galaxies that Webb has turned up since it began operating in 2022, a pattern significant enough that astronomers studying it have started referring to some of these objects informally as universe breakers, a term reflecting just how directly they challenge existing assumptions about how quickly galaxies can plausibly form and grow. MOEM Z14's own immediate predecessor is the distance record holder, a galaxy called JWST Z140, confirmed via a nearly 10-hour spectroscopic observation using Webb's NIR-SPEC instrument in January 2024, was itself already described by researchers at the time as shatteringly unexpected, sitting at a similarly extreme redshift and displaying its own version of the same core problem. A galaxy that appeared far too large, far too bright, and far too evolved for the amount of cosmic time it had actually had available to form. There's also a broader survey result worth including here, because it reinforces that MOEM Z14 isn't just a single strange outlier, but part of a systematic, measured pattern. A separate analysis, cited in coverage of the Discovery, found that the overall number of surprisingly bright distant galaxies Webb has now cataloged across its various deep field surveys appears to be roughly 100 times greater than what theoretical models had predicted going into the mission. That's not a modest, easily absorbed discrepancy that can be quietly patched with a small adjustment to existing equations. That's a systematic mismatch, showing up survey after survey, suggesting that something genuinely significant about the standard model of how the first galaxies formed and grew may need real revision, rather than minor tweaking around the edges. It's worth explaining, in a bit more depth, exactly how astronomers actually confirm a distance measurement this extreme, because the process itself is a genuine feat of engineering and careful science, not a casual estimate. Distance at these cosmic scales is measured using something called redshift, a phenomenon caused by the ongoing expansion of the universe itself. As light travels across billions of years from a distant galaxy to our telescopes, the expanding space it's traveling through stretches the light's wavelength along with it, shifting it toward the redder, longer wavelength end of the spectrum. The more a galaxy's light has been stretched the further away, and the further back in cosmic time that galaxy actually is. MOEM Z14 was measured at a redshift of roughly 44, meaning its light has been stretched by that same extreme factor over its multi-billion-year journey to Earth. Confirming a redshift that high requires Webb's NIR-SPEC instrument, a spectrograph capable of splitting a target's incoming light into its full spectrum of individual wavelengths, then precisely measuring exactly where specific, well-understood chemical emission signatures, such as the light naturally emitted by ionized hydrogen and oxygen, have shifted to. That process, similar to the nearly 10-hour observation NIR-SPEC previously conducted to confirm the redshift of MOEM Z14's own predecessor, JWST Z140, is what allows researchers to state a distance measurement with genuine scientific confidence, rather than a rough estimate based on brightness or color alone. It's also worth situating MOEM Z14 within an even broader, stranger pattern Webb has been quietly documenting since it began operations, one that goes beyond just the handful of individual record-breaking galaxies making headlines. Astronomers studying Webb's deep field surveys have identified an entire population of compact, unusually red objects nicknamed little red dots, found in surprisingly large numbers throughout the early universe, whose true nature remains only partially understood even now. Some of these objects appear to be powered by rapidly growing supermassive black holes, feeding at rates that seem difficult to reconcile with how much time was actually available for them to grow that large. Others may represent an early, unusually compact and dust-reddened phase of galaxy formation nobody had specifically predicted before Webb started returning data. Recent research has found that a meaningful fraction of these little red dots appear to fade or disappear entirely as the universe grows older, raising the further open question of what they eventually evolve into, with some researchers speculating they might represent a transitional stage on the path toward becoming the dense, ancient star clusters found orbiting galaxies like our own Milky Way today. Whatever the ultimate explanation turns out to be, the little red dot population represents yet another example of the same underlying pattern MOM-Z14 exemplifies. Webb keeps finding structures in the early universe that are more numerous, more evolved, or more energetically active than pre-launch theoretical models ever anticipated. It's worth walking through the honest range of ideas currently being discussed in the research community, because none of them so far has become a fully settled consensus, and that genuine ongoing uncertainty is part of what makes this such a compelling real story. One line of thinking suggests that star formation in the extremely dense, hot conditions of the early universe may simply have proceeded far more efficiently and rapidly than current models assume, allowing galaxies to build up large stellar populations, and therefore brightness, on a much faster timescale than the same physical processes would allow in the universe we see around us today. A related idea proposes that early galaxies may have gone through unusually intense compact bursts of star formation, concentrated into a much smaller volume of space than typical star-forming regions in more mature galaxies, which would help explain both the extreme brightness and the surprising compactness Webb is detecting together in the same objects. Some researchers have also raised the possibility that early supermassive black holes, growing and feeding unusually quickly at the centers of these young galaxies, may be contributing extra light to what Webb is detecting, artificially inflating how bright, and therefore how massive, these galaxies appear to be from a distance, a factor that could partially, though probably not entirely, help close the observed gap. None of these explanations has yet been confirmed as the full answer, and researchers studying this problem have been notably candid about that ongoing uncertainty in their own public statements. Wei Jinshen's own phrase, a chasm between theory and observation, is explicitly framed as an open, unresolved question the field still needs to work through, not a mystery anyone currently claims to have solved. That kind of honest, stated uncertainty from the actual researchers involved is worth appreciating on its own terms, because it's exactly the kind of scientific humility that gets stripped out of more sensationalized retellings of stories like this one, replaced instead with false, invented certainty in either direction, either declaring the standard cosmological model definitively broken or dismissing the anomaly as nothing worth taking seriously at all. The honest answer, as the scientists who actually did the work keep saying plainly, is that nobody yet knows for certain, and that finding out is going to require considerably more data. That's exactly what makes the pace of these discoveries so significant heading forward. Pennsylvania State University researcher Yijia Li, another co-author on the MOM-Z14 study, described the current moment in cosmology as an incredibly exciting time precisely because Webb keeps revealing the early universe in ways nobody anticipated, continually demonstrating just how much more there still is left to discover. That's a genuinely remarkable thing for a scientist to say about a result that, on its face, complicates their own field's existing theoretical framework. It reflects something true about how functioning science actually works when it's confronted by real unresolved data. Not defensiveness about a challenged model, but active enthusiasm about the fact that there's clearly more to learn and that the tools now exist to actually go find it. It's also worth remembering just how quickly this specific area of research has been moving. The original preprint version of the MOM-Z14 study was first released in May 2025, based on Webb observations gathered in April of that year. It took roughly 8 additional months of further analysis, peer review, and cross-checking before the finding was formally published and publicly announced by NASA in January 2026. In the time since Webb began its science operations in the summer of 2022, the record for most distant confirmed galaxy has already changed hands multiple times, each new record pushing the observational frontier further back toward the Big Bang itself, and each new record bringing with it the same basic pattern. A galaxy brighter, more massive, or more chemically advanced than existing theory comfortably predicted for an object that young. If that pattern continues, and researchers involved in this work seem to genuinely expect that it will, MOM-Z14 likely won't hold its own record for very long either. So here's the honest, complete picture behind a headline that, this time, genuinely does raise the troubling questions it claims to. James Webb has spotted a galaxy so far away that its light left home when the universe itself was less than 300 million years old, and rather than looking like the small, faint, barely formed object theoretical models predicted for that era, MOAM Z14 looks bright, compact, and chemically advanced in ways that shouldn't yet be possible according to our current best understanding of how galaxies form. Multiple named, credentialed researchers, publishing in a peer-reviewed journal, have described this finding using language like a growing chasm between theory and observation. Not because they're chasing headlines, but because that's genuinely, honestly, how they describe the scale of the discrepancy in their own published work and their own public statements. Nobody involved is claiming the Big Bang model itself is wrong. What they're saying, plainly and repeatedly, is that something about how quickly the first galaxies actually formed and grew appears to be meaningfully different from what decades of careful theoretical modeling predicted, and that figuring out exactly what that something is remains one of the most genuinely open, actively contested questions in modern astrophysics. That's the real story, and it needed no exaggeration to earn a headline about troubling questions, because actual credentialed cosmologists are using almost exactly that same language themselves, in their own peer-reviewed papers and their own public comments. Somewhere out past the edge of what any telescope had ever managed to see before sits a galaxy that, by every account, shouldn't look the way it does this early in the universe's history. And the scientists who found it aren't hiding that fact, or dressing it up for a video script. They're publishing it, discussing it openly, and treating it as exactly what it actually is. One of the genuinely biggest open puzzles currently sitting at the frontier of how we understand the origin of everything. There's a broader point worth sitting with here too about what it actually means for a scientific model to face this kind of pressure. The standard cosmological framework that predicts how galaxies should form, grow, and evolve over cosmic time isn't some fragile, casually assembled guess. It's built on decades of accumulated evidence, from the measured properties of the cosmic microwave background to the observed large-scale structure of galaxies spread across billions of light years, and it correctly predicts an enormous range of other observations astronomers have tested it against. Finding a genuine replicated anomaly like MOAM Z14 doesn't mean that entire framework collapses overnight. It means, more precisely, that some specific piece of the model, most likely something governing exactly how efficiently gas collapses into stars under early universe conditions, needs real refinement informed by exactly this kind of new observational pressure. That's not a weakness of the scientific process. It's the scientific process working as intended, using genuinely surprising new data to sharpen and correct existing theory, rather than simply forcing new observations to fit old assumptions, regardless of what the evidence actually shows. And that refinement is only possible because an instrument like Webb exists at all, positioned far enough from Earth's own heat and light interference to gather data of this quality, sensitive enough to detect a galaxy whose light has been traveling toward us since before our own solar system even existed. Every one of these record-breaking discoveries represents months of careful observation, painstaking data processing, and rigorous peer review before a single claim like MOAM Z14's redshift of 14. 44 is confidently published. That process is still ongoing right now across dozens of other Webb survey programs, currently gathering data on similarly distant targets. If the pattern established by JWST Z14-0 in 2024 and MOAM Z14 in 2026 continues, and researchers directly involved in this work have said plainly that they expect it will, the record will likely be broken again, possibly within the next year, revealing an even younger, even more surprising galaxy that will, once again, force cosmologists to ask exactly the same honest, open question currently sitting at the center of this entire story. How did the universe manage to build something this complex, this quickly?